So Jensen Huang, the CEO and founder of NVIDIA, gave a presentation at the AI Summit in India.
Hello, Mumbai!
As someone that's kind of spearheading the AI progress, he's got a really good vision about where things are going. In this video, he presents a few interesting concepts that are going to be pivotal to how AI is going to be developing moving forward and some of the infrastructure shifts that are going to be accompanied.
Get over here and hit like. This is no time to freeze.
To start off, Huang takes us back to 1964, if you can believe it, and the idea of general purpose computing. The CPU, the central processing unit, kind of the general purpose workhorse of the computer, and the improvements in which were largely driven by Moore's law. As our needs for computing improved, we were able to keep progressing, keep doing things because of Moore's law and the rapid advancement in the processing power in the CPU. However, now we're reaching the limits of Moore's law. We can't just keep cramming more transistors onto a chip and expect the same exponential growth. So then what is the next big leap for computing, especially regarding AI? This is where accelerated computing comes in. We're all aware of GPUs, graphic processing units, like the NVIDIA graphics card that a lot of us use to play video games. And Huang argues that the idea of accelerated computing is that new free ride. Much like Moore's law was for general purpose computing, accelerated computing for specific processes, it's what's going to be driving the advancement moving forward. Take a listen.
We know now that the scaling of CPUs has reached its limit. We can't continue to ride that curve, that free ride. The free ride of Moore's law has ended. We have to now do something different, or depreciation will end. And we now will not enjoy depreciation, but experience inflation, computing inflation. And that's exactly what's happening around the world. We no longer can afford to do nothing in software and expect that our computing experience will continue to improve, that costs will decrease, and continue to spread the benefits of IT and to benefit from solving greater and greater challenges. We started our company to accelerate software. Our vision was there are applications that would benefit from acceleration if we augmented general purpose computing. We take the workload that is very compute intensive and we offload it and we accelerate it using a model we call CUDA, a programming model that we invented called CUDA that made it possible for us to accelerate applications tremendously. That acceleration benefit has the same qualities as Moore's law. For applications that were impossible or impractical to perform using general purpose computing, we have the benefits of accelerated computing to realize that capability. For example, computer graphics. Real-time computer graphics was made possible because of NVIDIA coming into the world and make possible this new processor we call GPUs. The GPU was really the first accelerated computing architecture running CUDA, running computer graphics, a perfect example. We democratized computer graphics as we know it. 3D graphics is now literally everywhere. It could be used as a medium for almost any application. But we felt that long-term, accelerated computing could be far, far more impactful. And so over the last 30 years, we've been on a journey to accelerate one domain of application after another. The reason why this has taken so long is simply because of this. There is no such magical processor that can accelerate everything in the world. Because if you could do that, you would just call it a CPU. You need to reinvent the computing stack from the algorithms to the architecture underneath and connect it to applications on top. In one domain after another domain, computer graphics is a beginning, but we've taken this architecture, CUDA architecture, from one industry after another industry after another industry. Today, we accelerate so many important industries.
There was a bit of an effect of slowing down AI adoption because some of the software needs to be rewritten. He introduces this idea of software 2.0. Now, I've heard this concept first on an old blog post by Andrej Karpathy, where he talks about, software 1.0 and moving into software 2.0. And the idea was that before, humans wrote the algorithms, the code, everything was written out step by step. It was explicit instructions telling computers what to do. In contrast, Software 2.0 is based on machine learning. No longer are humans writing the code. Take a listen to Huang talk about this phenomenon, and as you do, think about this. If the jump from Software 1.0 to 2.0 was, instead of humans writing code for computers, now AI writes the code for computers, then what is the next logical step? What is Software 3.0?
The world has completely changed. Now let's think about what happened. The first thing that happened, of course, is how we do software. Our industry is underpinned by the method by which software is done. The way that software was done, call it Software 1.0, programmers would code algorithms, we call functions, to run on a computer. And we would apply it to input information, to predict an output. Somebody would write Python or C or Fortran or Pascal or C++, code algorithms that run on a computer. You apply input to it, and output is produced. Very classically, the computer model that we understood quite well. And it, of course, created one of the largest industries in the world, right here in India, the production of software. Coding, programming became a whole industry. This all happened within our generation. However, that approach of developing software has been disrupted. It is now not coding, but machine learning. Using a computer to study the patterns and relationships of massive amounts of observed data to essentially learn from it the function that predicts it. And so we are essentially designing a universal function approximator using machines to learn the expected output that would produce such a function. And so going back and forth, this is Software 1.0 with human coding to now Software 2.0 using machine learning. Notice who is writing the software. The software is now written by the computer. And after you're done training the model, you inference the model. You then apply that function now as the input, that function, that large language model, that deep learning model, that computer vision model, speech understanding model, is now an input neural network that goes into the GPU that can now make a prediction given new input, unobserved input. This way of doing software, notice, is based on fundamentally machine learning. And we have gone from coding to machine learning, from developing software to creating artificial intelligence, and from software that prefers to run on CPUs to now neural networks that runs best on GPUs. This, at its core, is what happened to our industry in the last 10 years. We have now seen a complete reinvention of the computing stack. The whole technology stack has been reinvented. The hardware, the way that software is developed, and what software can do is now fundamentally different. We dedicated ourselves to advance this field.
Next, they talk about the concept of a universal function approximator. Now, Jensen has talked about this idea before, and basically you just think of AI as, tokens in and tokens out. The ability of deep learning of these models to learn virtually any type of information, whether it's images, text, audio, can be chemical structures, protein sequences. We've seen that with AlphaFold and AlphaProteo. In fact, the Google DeepMind team behind that model recently won the Nobel Peace Prize for chemistry and promises some pretty big breakthroughs in proteomics, right? Learning how proteins work, what functions they have. And now we're even beginning to create designer proteins, custom proteins, which are the building blocks of life. And humans now are finally, with the assistance of these AI models, are beginning to design these building blocks of life. But the idea is that we can put in anything, images, text, audio, protein sequences, and these models can grasp the underlying patterns and relationships, regardless of what data we're talking about. And this versatility kind of explains the Cambrian explosion, if you will, of AI startups leveraging these techniques. Much like the rapid diversification of life during Earth's Cambrian period, we're seeing this new surge of AI applications in companies powered by deep learning. So far, we're seeing it with images, text, audio. Like I said, we've seen things like Sumo producing their very own music, AI-powered music. We've seen a lot of AI video startups. But we've also seen the start of startups that are doing their work with proteins, with life, with biology, a combination of AI and bioengineering. And this is just sort of the first and second wave. Keep in mind, we don't really know if there's a limit to what these AI models can understand. They can produce the underlying patterns and relationships of data. How far can we take that?
A massive system designed to study data at an enormous scale so that we could discover patterns and relationships and learn the meaning of the data. This is the Greek breakthrough. In the last several years, we have now learned the representation or the meaning of words and numbers and images and pixels and videos, chemicals, proteins, amino acids, fluid patterns, particle physics. We have now learned the meaning of so many different types of data. We have learned to represent, how to represent information in so many different modalities. Not only have we learned the meaning of it, we can translate it to another modality. So one great example, of course, is translating English to Hindi. Translating English, large body of text, into other English, summarization. From pixels to image recognition. From words to pixels, image generation. From images, videos, to words, captioning. From words to proteins used for drug discovery. From words to chemicals, discovering new compounds. From amino acids to proteins, understanding the structure of proteins. These fundamental ideas, essentially a universal translator of information from any modality to another modality, has led to a Cambrian explosion of the number of startups in the world. They're applying the basic method I just described. If I could do this and that, what else can I do? If I can do that and this, what else can I do? The number of applications has clearly exploded. In the last couple, 2-3 years, the number of generative AI companies around the world, tens of thousands, tens of billions of dollars have been invested in this field, all because of this one instrument that made it possible for us to study data at enormous scales.
And finally, we start talking about AI agents. Jensen is very excited about the potential of these super employees, as he refers to them as, that are powered by AI. AI agents can go beyond passive information processing. They're more than your Excel spreadsheet. They actively work on tasks. They make decisions. They even collaborate with other AI agents. Now, this concept might sound like science fiction, but Huang provides compelling examples. We can have marketing agents that analyze data. They can craft targeted campaigns. They can write ad copy. We can have customer service agents handling complex inquiries and providing personalized support to your customers 24/7. He even mentions some AI agents that are used internally by NVIDIA for chip design. We've seen Dr. Jim Fan talk briefly about this, the idea that the next generation of AI hardware will be designed by AI itself. We will be using AI to help us design the very chips, the very hardware, the infrastructure that AI will run on. And so Huang believes that these agents could handle roles that require creativity, for example, strategic thinking, certainly technical expertise. And this is going to raise intriguing questions about the future of work for humans, for us. Are we obsolete? Are we out of jobs? Now, Huang believes that AI agents will not replace humans, but will rather augment us, creating a new breed of super employees, so to speak. Now, you can just imagine having a team of skilled AI assistants handling a lot of the various tedious tasks for you. That's going to free you up to focus on higher level thinking and creative problem solving. By harnessing AI, you reduce the sort of tedious day-to-day annoying tasks, the cognitive load of those little tasks, and you're allowed to free up your mental energy for higher level thinking. And to create these super employees, Huang outlines the agent lifecycle, training AI with massive amounts of data to learn necessary skills, fine-tuning the agent's behavior to fit specific business needs. He's saying you're not going to use your marketing agent to handle customer service for you, for example. And then we have to evaluate performance to ensure expectations are met, establishing guardrails and safety protocols to ensure ethical and responsible operation. And this process is going to mirror traditional employee training and onboarding, but it's going to occur in the digital realm, which is where he mentions the next big thing that NVIDIA has to offer. But here's the clip about AI agents.
This is a time now where the large language models and the fundamental AI capabilities have reached a level of capabilities we're able to now create what is called agents. Large language models that understand the data that, of course, is being presented. It could be streaming data, it could be video data, language model data, it could be data of all kinds. The first stage is perception. The second is reasoning about, given its observations, what is the mission and what is the task it has to perform. In order to perform that task, the agent would break down that task into steps of other tasks. And it would reason about what it would take, and it would connect with other AI models. Some of them are good at, for example, understanding PDF. Maybe it's a model that understands how to generate images. Maybe it's a model that is able to retrieve information, AI semantic data from a proprietary database. So each one of these large language models are connected to the central reasoning large language model we call agent. And so these agents are able to perform all kinds of tasks. Some of them are maybe marketing agents, some of them are customer service agents, some of them are chip design agents. NVIDIA has chip design agents all over our company helping us design chips. Maybe they're software engineering agents. Maybe they're able to do marketing campaigns, supply chain management. And so we're going to have agents that are helping our employees become super employees. These agents, or agentic AI models, augment all of our employees to supercharge them, make them more productive. Now, when you think about these agents, it's really the way you would bring these agents into your company is not unlike the way you would onboard someone who's a new employee. You have to give them training curriculum. You have to fine-tune them, teach them how to use, how to perform the skills, and understand the vocabulary of your company. You evaluate them, and so there are evaluation systems, and you might guardrail them. If you're an accounting agent, don't do marketing. If you're a marketing agent, don't report earnings at the end of the quarter, so on and so forth. And so each one of these agents are guardrailed. That entire process we put into essentially an agent lifecycle suite of libraries, and we call that NeMo. Our partners are working with us to integrate these libraries into their platforms so that they could enable agents to be created, onboarded, deployed, improved into a lifecycle of agents. And so this is what we call NVIDIA NeMo. We have, on the one hand, the libraries. On the other hand, what comes out of the output of it is an API inference microservice we call NIMs. Essentially, this is a factory that builds AIs. And NeMo is a suite of libraries that onboard and help you operate the AIs. And ultimately, your goal is to create a whole bunch of agents.
Now, of course, the next big thing after we sort of expand the digital world, the omniverse, right? There's the physical world. And when it comes to AI interacting with the physical world, Huang introduces the concept of physical AI. So if you think about physical AI plus robots, that is the bridging of the gap between the digital and the physical. And NVIDIA has 3 types of computers for that sort of AI. We have the DGX systems for AI training, Omniverse as a platform for simulation and creating digital twins, and the Jetson AGX platform for deploying AI into the real world. Digital twins are virtual replicas of physical objects or environments, enabling AI to experiment and optimize processes in a virtual setting before implementing them physically. This approach allows for training robots to perform complex tasks, testing new manufacturing layouts, and simulating disaster scenarios. And this all takes place within a dynamic, physics-obeying digital environment. It's the real world simulated with actual employees, with, injuries, all the physics and all the complications of the real world.
What happens after agents? Now remember, every single company has employees, but most companies, the goal is to build something, to produce something, to make something. And those things that people make could be factories, it could be warehouses, it could be cars and planes and trains and ships and so on and so forth. All kinds of things. Computers and servers, the servers that NVIDIA builds, it could be phones. Most companies in the largest of industries ultimately produces something. Sometimes production of service, which is the IT industry, but many of your customers are about producing something. That next generation of AI needs to understand the physical world. We call it physical AI. In order to create physical AI, we need 3 computers, and we created 3 computers to do so. The DGX computer, which Blackwell, for example, is a reference design, an architecture to create things like DGX computers for training the model. That model needs a place to be refined. It needs a place to learn. It needs the place to apply its physical capability, its robotics capability. We call that Omniverse, a virtual world that obeys the laws of physics, where robots can learn to be robots. And then when you're done with the training of it, that AI model could then run in the actual robotic system. That robotic system could be a car, it could be a robot, it could be a autonomous moving robot, it could be a picking arm, it could be an entire factory or an entire warehouse that's robotic. And that computer we call AGX, Jetson AGX, DGX for training, and then Omniverse for doing the digital twin.
And now the leap from digital twins to the physical world is going to be achieved through the Jetson platform, which is a smaller embedded system designed to run AI directly in robots and autonomous machines. This integration results in applications like self-driving cars, robots working in factories and warehouses, handling delicate tasks and collaborating seamlessly with human workers. And once again, physical AI is not seen as a replacement for humans, but rather a means to augment our human capabilities, making us more efficient and productive. The robots can handle the heavy lifting, the repetitive tasks, allowing humans to focus on quality control, problem solving, and specialized tasks that require ingenuity and dexterity.
Hello, I'm James, a digital human.
Industrial enterprises use physical AI to automate physical work. Physical AI embodies robots like self-driving cars that safely navigate the real world, manipulators that perform complex industrial tasks, and humanoid robots who work collaboratively alongside us. Plants and factories will be embodied by physical AI, capable of monitoring and adjusting its operations, or speaking to us. NVIDIA builds 3 computers to enable developers to create physical AI. The models are first trained on DGX. Then, the AI is fine-tuned and tested using reinforcement learning physics feedback in Omniverse. And the trained AI runs on NVIDIA Jetson AGX robotics computers. NVIDIA Omniverse is a physics-based operating system for physical AI simulation. Robots learn and fine-tune their skills in Isaac Lab, a robot gym built on Omniverse. This is just one robot. Future factories will orchestrate teams of robots and monitor entire operations through thousands of sensors. For factory digital twins, they use an Omniverse blueprint called Mega. With Mega, the factory digital twin is populated with virtual robots and their AI models, the robots' brains. The robots execute a task by perceiving their environment, reasoning, planning their next motion, and finally converting it to actions. These actions are simulated in the environment by the world simulator in Omniverse, and the results are perceived by the robot brains through Omniverse sensor simulation. Based on the sensor simulations, the robot brains decide the next action, and the loop continues, while Mega precisely tracks the state and position of everything in the factory digital twin. This software-in-the-loop testing brings software-defined processes to physical spaces and embodiments, letting industrial enterprises simulate and validate changes in an Omniverse digital twin before deploying to the physical world, saving massive risk and cost. The era of physical AI is here, transforming the world's heavy industries and robotics.
So what do you think? Is this an exciting time to be watching this unfold? Do you think Jensen is correct about all the stuff that he's doing, his vision for AI moving forward? Let me know in the comments. If you made it this far, you're a trooper. Thank you so much for watching. My name is Wes Roth, and I'll see you in the next one.